This video is part 5 in my video series designed to help you get ready to take organic chemistry. And in this video, I'm going to be reviewing Bronsted-Lowry acids and bases because a lot of the chemical reactions that we study in organic chemistry are acid-base reactions. Now, I'm going to begin this video by reminding you of the definition of a Bronsted-Lowry acid and a Bronsted-Lowry base, and then we're just going to jump into some examples of acid-base reactions. A Bronsted-Lowry acid is defined as a molecule that donates an H+ ion in a chemical reaction, and a Bronsted-Lowry base is defined as the molecule that accepts or takes the H+ from the acid. Now, I do want to introduce some terminology before we jump into our examples. I want to introduce some terminology that you probably weren't introduced to in general chemistry. First of all, proton. This is the nickname that we give to the H+ ion in organic chemistry. So we'll use this term all of the time. We talk about protons, we say proton instead of saying H+ ion, and I'm going to try to use that term in this video to help you get used to it. The term proton also gives rise to a couple other terms. Deprotonation, which is the term that we use to describe the process of removing a proton or removing a hydrogen ion from a molecule. So we might say, oh, in this chemical reaction, this molecule, this acid, is being deprotonated, which just simply means that its hydrogen ion is being removed. Also, we have the term protonation, which is the term that we give to the process of adding an H+ ion or adding a proton. So we might say, oh, this base is being protonated, which means that it's having an H+ ion added to it. And again, I'm just going to try to use these terms in this video to help you get comfortable with them. Now, moving on to some sample acid-base reactions, I'm going to start with one that you probably saw quite a bit in Gen Chem. That's going to be HCl, strong acid, reacting with water. And I'm actually going to be drawing these as Lewis structures just to kind of help us visualize the reaction. In Gen Chem, you probably just wrote it out using molecular formulas like this. You probably didn't think about it in terms of Lewis structures, but we're going to be looking at the Lewis structures. Now, in this reaction, HCl we know is the acid. HCl is one of the 7 strong acids: hydrochloric acid, HCl, HBr, HI, HNO3, etc. This is definitely an acid, which means that the hydrogen of HCl is going to be donated over to the water molecule. So we could say that the HCl is going to be deprotonated because its hydrogen ion is going to be removed, or its proton is going to be removed. When the proton is removed from the HCl molecule, it only takes the hydrogen ion. It does not take the electrons in the HCl bond. So these 2 electrons in the HCl bond, they stay associated with the chloride. It becomes a chloride ion, and that leaves it as that chloride ion. It's going to have 4 lone pairs around it. It's got the 3 that it already had, and the electrons in the HCl bond, they stay associated with that chloride. That gives that chloride ion a negative charge. And then the other product of this reaction is going to be our proton moving over to the water molecule. It actually bonds to the oxygen in the center, so it's going to give us something that looks like this. Only 1 lone pair on that oxygen because one of the lone pairs on the oxygen is used to create that new bond to the hydrogen. So HCl is our acid in this reaction. Water is our base, and in Gen Chem, you probably just wrote it out something like this. But here we're getting a better picture of the bonds that are being made and the bonds that are being broken in this reaction. Let's take a look at another acid-base reaction that you probably saw in Gen Chem, but again, we're going to be drawing it with Lewis structures. Again, the reason that we want to do this is because it gives us a little bit of a visual of the bonds that are breaking and the bonds that are being formed in the reaction. This is acetic acid. You definitely saw this all the time in Gen Chem. In Gen Chem, you may have written it as CH3CO2H or CH3COOH or HCH3CO2 or HC2H3O2. There's a lot of different ways that we write this molecule. But acetic acid is definitely one that you were introduced to in Gen Chem. And in acetic acid, this is the acidic proton. So that means that calling this the acidic proton, that means that this is the hydrogen that actually gets donated in the acid-base reaction. In organic chemistry, you are going to learn how to tell which of the hydrogen atoms in a molecule is the one that gets donated in an acid-base reaction. We're not going to go over that in this video. We'll save that for ochem. Let's react this acetic acid, this is our acid, let's react it with the ionic compound NaOH. Now before we predict the products of this reaction, let's talk a little bit about NaOH. NaOH is an ionic compound, as I said. It's made up of the sodium cation and the hydroxide polyatomic ion. There. And in Gen Chem, you probably got familiar with the term spectator ion. Spectator ions are ions that are not participating or are not involved in a chemical reaction. Sodium ion is a spectator ion, meaning that in this particular reaction is not actually doing any chemistry. And in organic chemistry, we really just like to focus on the atoms and the molecules and the ions that are doing things. So in ochem, we are going to not write out the whole entire NaOH molecule. We're just going to focus on the hydroxide ion, the part that's actually doing the chemistry. And you're going to see this quite a bit in ochem, where we'll just write a molecule and we won't even write what that cation might be, because honestly, we just kind of don't care. So here are the acid and base for this next reaction. We've already identified the acidic proton of our acid. We want to draw what that molecule will look like after it gets deprotonated. So what we want to do is break the oxygen-hydrogen bond, and the electrons in the oxygen-hydrogen bond are going to stay associated with the oxygen atom because this hydrogen leaves as a proton, an H+ ion. It's not taking any electrons with it when it goes. That proton is going to go over to the hydroxide ion. The hydroxide ion is going to get protonated, meaning that it's going to have that H+ added to it. The H+ is going to add itself to one of the lone pairs on the oxygen. I'll just pick this one right here. This lone pair is going to be used to form a bond to that hydrogen ion, like that proton. I'm actually going to color this one red, and I'm going to color this one red too to match up. Okay, let's look at another example. This time I'm going to show you an acid that you probably did not see in Gen Chem. This molecule right there, its acidic hydrogen is this guy here on the end. This is an acid, and we are going to react this guy with a different base. So we're going to react it with, I'm going to get really creative here. This is our base, like that. So this is really typical of an acid-base reaction that we might represent or think about in organic chemistry. So first of all, again, I am telling you that this molecule is the acid, and I'm also telling you specifically that this is the acidic proton in the molecule. And when you get into ochem, you will learn how to predict whether or not this molecule is an acid, and you'll also learn how to predict which hydrogen is the acidic one. We're not worrying about that today. I'm just straight up telling you this is our acid. So let's begin by drawing what this molecule looks like after it has been deprotonated. So remember, all that we're going to be doing is removing that last hydrogen, that red hydrogen, and it is leaving as a proton, as an H plus ion, which means it's not taking those electrons with it. It's not taking any electrons with it. And the electrons in that carbon-hydrogen bond are going to become a lone pair of electrons on that carbon. That carbon with a lone pair, 3 bonds and a lone pair, is a carbon with a negative formal charge. That's one of the common bonding patterns that we learned a while ago. A carbon with 3 bonds and a lone pair, negatively charged carbon. And that proton is going to be transferred over to our base. It is going to bond itself to the oxygen with the negative formal charge, just like we saw in the previous example where the hydrogen bonded itself to that oxygen. Also, just like we saw in the first example, even though in this case the oxygen didn't have a negative charge, that's still where the hydrogen went anyways. So one of the lone pairs on this oxygen is going to be used to create a bond to that acidic hydrogen, and that is going to give us this molecule right here, and I'm going to color in that red hydrogen. And these, if you can get comfortable with drawing the structures of acids after they've been deprotonated and drawing the structures of bases after they've been deprotonated, that is, I'm giving a thumbs up right now even though you can't see it, that's a good skill to have as you're coming into organic chemistry.